And greetings, friends. Happy Tuesday, or whatever day it is to you when you are watching this. We are starting week 7 here, and we have transitioned into thermodynamics, which is our second major topic for this class here. So, in terms of PLC, I have not actually posted it yet. At least as of right now, which may be different for you when you watch this, but by then it will be. So good news. It's going to be on thermodynamics this week, despite the fact we do have celebration coming up on Thursday. So we'll have a thermo PLC just to get things kicked off. That will, as usual, be for Friday. And then homework 3 and celebration 1 will occur on Thursday of this week. So please do put the finishing touches on the homework and study up and be ready for the celebration. And we'll do both of those Thursday. The celebration on Thursday will mean we will not actually have class Thursday, so there will only be 2 videos of class this week, and then I'll do a lab on Friday as usual. Celebration should be open. If I've done things correctly, then it should be open pretty much the entire day, and you can pick your time and get moving. So just the usual words of caution when it comes to celebration. Make sure you're in a place where it's conducive to doing work, and you have a relatively stable internet connection, and you are pretty well practiced in the picture taking and or slash PDF submitting of documents, which I think most of you pretty much are. So remember that the time that you're going to get for that is going to be, I think it's about nominally, it's going to be a 2-hour situation unless there's changes, unless you have changes made to that. But we'll look for about a 2-hour. That does include starting and finishing time. There's no like extra time for submitting, it's included. So just make sure that you've built that in, and I would probably try to keep yourself to a relatively brisk pace in order to keep yourself on track. All right, so think about your time. Don't get lost in one problem, because you'll be working on it and look up and it'll be an hour and a half later and you'll go, oh no, I got 900 other ones to do. Yes, not really, but that's okay. All right, so usual words of caution with respect to that. In terms of words to talk about, solutions, remember I am looking for pictures. So when you're thinking about the topics that we've talked about, I made that list of topics last time. Think about the drawings that go along with those, right? We have ray drawings for the lenses, the mirrors. We have Snell's law has refraction and total internal reflection. We have things like path length differences. Should a wavelength change, you could represent that as a slightly shorter wavelength inside a medium versus outside, or something like that. The pictures are generally fairly, in that sense, simplistic, but we do use them to communicate understanding. And ultimately, my job is to try and assess your understanding, and that is hard to do if you don't communicate it well. All right, so you might have a great understanding, but if I can't get that sense, then I can't work with what you think is your understanding, right? So try to make sure that you're communicating. One of the big ways of doing that in the way I do things is by drawing the pictures. So please be sure to keep that as a priority in your mind when you are solving problems on the celebration. Don't just jump straight to math, okay? Or if you do it down here and then go back and fill in a picture up here later. So whatever works with your workflow, it's all coming to me at the same time, so I can't tell what you did first, okay? Last thing I will suggest is to think of, I don't know, maybe this is not quite this is not quite comprehensive enough, but I would say think of a solution as a 3-part situation, right? There's a picture representation, there's a math representation, and then there's kind of the interpretation at the end representation, where Sometimes we don't need to do this, but on questions where it's a ranking or questions where there isn't a lot of calculation to do, but you're going to come up with an answer, I want you to explain the answer. Okay? And I'm kind of leaving that up to you folks and saying, I'm going to put the expectation there that wherever there's a problem and it says, do this, make sure that you put down enough to make me aware that, hey, I know all this about how to do a problem like that, right? So if it's a ranking and you just write A, C, B, D, well, I don't, okay, but I don't get anything from that. You haven't shown me anything, right? I can't, my job is to assess your understanding. If you just do that, even if it's correct, you could have guessed it. I don't know, right? So always include some type of explanation if it's a conceptual type of question, if it's a ranking question, if it's something like that, whereby it's not going to be, for example, find the image distance from the lens or something like this, and it's magnification, right? Where you're coming out with something very solid from a math perspective. If it's something like more conceptual, well, include a conceptual solution, all right? So anyways, there's a little bit to think about. Those are some of the things that I consider when I'm going through and trying to grade these. Maybe you have math mistakes. I'm not so concerned about that. I'm more concerned about what the physics is that you're showing me, right? That's right. That's the basis of the class. It's not a math class. So anyways, when it comes to that, go do good work. What do you want me to say? Do physics, okay? When we left off last time, when we left off last time, we had just started the laws of thermodynamics, so I will work here for a comprehensive. Set, so we have them all on the board at the same time. Law 0, as we talked about last time, deals with thermal equilibrium and the establishment of a temperature or some type of, it doesn't have to be temperature, it could be anything, right? I could have a balloon and I could be looking at the measurement of the volume of the balloon or something like that. I could hold it against a block of ice and watch it kind of, it'll shrink down a little bit, and then I could hold it against this other thing and see, does it stay the same size, right? And by that, I infer that these two things have the same temperature. And if it doesn't, then they don't, right? So, excuse me. So we have a way of defining temperature through Law 0, and like I said last time, it's basically scaffolding so that we can actually have conceptual understanding go on and work within the other laws. So Law 1 is energy conservation in the sense that we are interested in internal energy, okay? So internal energy of a system. We're not so much concerned with mechanical external energies, like what if I have this box of gas and it's on a jet plane and it's flying along, it has all this extra macroscopic kinetic energy. We're not concerned with any of that. We're generally concerned with the internal energy. So if I heat this box of gas, or is it right? If I have a balloon and I compress it or something like that, whether I do that at rest on Earth's surface or on a skateboard or in a car or in a jet plane, I'm going to talk about the internal energy of the gas. It'll work the same way, right? I'm not concerned with overall relative motion or whether I'm high up in a gravitational field or moving or anything like that. That's all dealt with mechanically, right? So that's like a 4A topic. We dealt with that already. We're dealing with the internal energies now. So we're going to talk about internal energy, and the way we change the internal energy of a system is going to be via either heating it, right, by having a heat transfer, or by doing work on the system. Like literally, I talked about compressing the balloon, right? That's exerting a force through a distance. All right, so the internal energy changes via either heat transferred or work done. All right. Okay. Okay. All right. Okay, so that was approximately where we were on at the cessation of our time last week. So I have a few things to add regarding Law 1. I talked to you a little bit about the idea of the establishment of a system so that you can more appropriately talk about what are the changes that you expect in the system. So how is the system's internal energy changing? How is the system reacting to heat that's being transferred to or from, or work being done to or from? So we come up with the idea that we need to think about a system for this. Okay, so I'll just say system here, and its boundaries. Oops, not that way. It's pen. This pen cannot spell. Okay, the system and its boundaries. In other words, are we going to allow heat to pass into the system? Yes. Okay, well, that's called a diathermal boundary. All right. If we are not, a diathermal boundary allows heat transfer. If we don't think about that, it's called adiabatic. And that means no heat transfer. No heat. Yeah, let's say no heat transfer. Are they rigid? Are the boundaries rigid? Are they fixed? That would mean no work, right? Or are they flexible? In which case you could deform the system and do work on it by compressing it or by expanding it or something like that. All right. So thinking about the system and its boundaries, we come to this situation here where we've talked about the conservation of energy, and basically, like I said, we're thinking of the internal energy of a system. All right. Okay. So I think that pretty much talks about what I wanted to talk about with Law 1. So we were there. I want to go into. Actually, I want to do one other thing with energy conservation. I want to do one other thing talking about this. Just from a historical perspective, it's kind of fun to think about this. Back in the early 1800s, they didn't know that heat and work are actually forms of energy going from one place to another. They thought they were different things. Heat, they thought of as kind of a fluid that flowed, and work was more of a you did work. You exerted yourself, right? Or a horse pulled a plow. It did work. So an interesting little piece comes to this where we find that the effects of heat and work are found to be the same. Okay, so here is a big vat of, say, water, okay? And it's got a set of paddle wheels in here, all right? So you could just stand up here and it's like a blender, like a churning, you'd be churning it, okay? So for example, you could, in fact, take this thing, hook it up to a little mass, right? The mass M. As it drops down, it unwinds, and the spool here turns the paddles, okay? So you would say, oh, that weight has dropped and done work, right? There's a force exerted through a distance, and there was work done by the weight on the water effectively, right? Because the paddles were spinning in the water. And what did we find? We find that the water heats up. But that's kind of weird because we haven't heated the water up. Now, okay, this might seem pretty obvious to us nowadays, but 200 years ago, 200 years ago, I was going to say 150, but it's not that anymore. About 200 years ago, they had no idea. Okay, so they thought, wow, how can the water be heating up when there's no heat? Okay, so work is done by the falling mass. Work is done on the water, okay, by the falling mass. And therefore, what happens is we say that the mass did work, the water's energy has increased, right? But it's an internal energy. It's not like the water's suddenly moving around with kinetic energy and going that way or something like that. No, it's the internal energy. Its temperature has increased, right? So that's an internal energy. So what we have here then is the equivalent of having heated this thing with a flame. Okay, so that is a mechanical equivalent of heat. Because the water heated up, right? So work done on the water by the falling mass causes the water to warm up. So we'll say the water's temperature increases. And that was kind of surprising because, like I said, it was surprising to them because there's no flame here. There's no heat going into the water, but yet the water's temperature is higher. So there's a mechanical equivalent of heat, which turns out to be, as we know now, approximately, it's 4.186. We'll just round to 4.2 joules per calorie. And that's because when we talked about, or when they talked about in the early 1800s, when they talked about work, it was done in joules, because Joule was the guy who came up with this setup. This is the Joule apparatus. It does work, okay? But you measure work in joules now. When you measure heat transfer, you measure it in calories, because they thought heat was a fluid, and they called it caloric. Okay, so the 4.2 joules, you would do 4.2 joules of work in order to increase the temperature of the water, the same amount that 1 calorie of heat input would increase the temperature of the water. By a fun and interesting choice of units, you might recognize that as the specific heat of water, because the specific heat of water is 1 calorie per gram, and therefore it's 4.2 joules. And if you have no idea what I'm talking about, don't worry, we'll talk about this a little bit more in depth later. But nonetheless, there's that. So the specific heat of water in joules is 4.2 joules per gram. Well, that's actually not specific. Okay, per gram per centigrade, right, to be specific. Okay, so that was the experiment that helped people realize that work and heat had the same effect, all right? And therefore, when we talk about something like this, it comes out in mathematical form that the internal energy change is equal to Q plus W. That's the mathematical representation of the first law. Work, W. Q, heat. I know, sorry. I apologize now. And I will probably do that again later. But nonetheless, heat plus work. All right, let's go to law 2. Now, law 2 is pretty crazy. Okay, law 2 is, but it's great, all right? It really is very good. It comes in several varieties. So I'm going to give you a couple of the varieties because there have been a couple of people who did significant work on this. And so I would like to introduce you to that in the sense that the things that they said actually helped shape our thinking about what the second law is telling us. All right. So we'll start with the well, chronologically, we should start with the Carnot. So we'll start with the Carnot statement. The Carnot statement. I will also tell you the Kelvin statement and then also the Clausius statement, just to give you some perspective on what people think about the second law. So Carnot basically said that, let me get the wording right here. So, okay. And there's a couple of different things in here that we're going to have to talk quickly about. But for example, when I say a cyclic process, I mean something that's repeating itself. Okay. And when I say repeating itself, I mean it undergoes some change in its internal energy and its state variables, right? Because remember, we've defined the system. And so if it's a gas, maybe the pressure and the volume have changed somehow, but it's a cycle. So it goes through, changes the pressure, changes the volume, temperature, blah, 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 and then returns to its original values. And that's the key that makes it a cyclic process, okay? That return to its original state, okay? So it's something that repeats, that always comes back to where it started, and then it does it again, and then it does it again, and it does it again, like that, okay? So you can think of it as kind of like an engine, but okay, we'll get there. A cyclic process. So Carnot says that if you take a process like that repeats itself back to its original variables, and its only function, whose only result, yes, is to exchange. This should be exchange, not extract. I like how they use fewer than two instead of just saying one or none. Okay, now we get to the words that are really meaningful here. Okay, so this is the Carnot statement, and ultimately Carnot was the guy who first started thinking about, okay, look, we've got this first law. We've got the energy conservation, okay? Remember, he didn't actually think that because he preceded the first law by about 20 years. Nonetheless, suppose, for the sake of a good story here, a good storyline, that he's trying to figure out how to take heat and make it useful, right? In other words, most of the main function of an engine is to take in heat and produce work. In other words, instead of having a horse plow your fields, why not burn some wood, heat some water up, and then have it run a motor and then propel this thing up and down your fields, and it'll be done way quicker. So the idea was that they were just coming to this point in time where the Industrial Revolution was just about to start kicking into high gear, and the idea of how to get engines to do the work of people was really just getting developed, right? So this is one of the major developments that happened. How do you take heat and make it into work? Make this engine do something for us, right? So that I can go relax. And instead of having to sit on have the ox pulling the plow and I've got the till and I'm steering and all this stuff, instead I'll just let the motor do everything, and I'll go back and sit with a brandy snifter in my robe and slippers next to the fire and read a good book. All right, so that's kind of where they were going with this type of thing. All right. If I draw this out, what it looks like, okay, it's going to have a couple of components to it. So number one, let's do this here. I'm going to have to figure out what's a heat reservoir. Okay. So I've got this cyclic process. Okay. So I've got something that's going to repeat itself. All right. For example, one of the typical things we have to think about something that's cyclic is a piston with a cylinder. Right. So what I'm going to do is I'm going to say, okay, I can, for example, measure the volume of the air, and I'll make this a little bit higher here. Okay, so I've got some volume of air. I know this is kind of hard to see, but there's the piston right here, and there's a volume of air underneath it. And I'm going to consider that. So I'm going to say, okay, it's got some volume. I could measure the pressure. I could measure the temperature. I'm not going to let any in or out. So I'm not going to suddenly have the amount of stuff change. And I'm going to say, all right, I'm going to put a mass on top of here. Or it's going to go like this. It's going to compress, right? And then I'm going to take this and I'm going to cool it off. I'm going to change its temperature. And then I'm going to heat it way up. And then I'm going to say, okay, and I'm going to load more mass on. Okay. Oh, look, it's back to where it started. That's a cyclic process. Okay. So thinking of a piston cylinder is, I think, a useful visualization tool when you're coming to think about, well, what are we talking about here? We're talking about the gas in a cylinder being compressed or heated or expanded or something by a piston, okay? So a cyclic process, and if their only result of that process is to exchange heat with fewer than 2 heat reservoirs. Now a heat reservoir, for example, the atmosphere, that's a heat reservoir. We can dump heat into the atmosphere. We can take heat out of the atmosphere, and it doesn't really change temperature very much. Okay, in principle, yes, it does, but it's so large. Same with the oceans, right? I could dump a cup of boiling water into the ocean. Did I just change the ocean's temperature? Probably not. Okay, so those things are our mental models of what's a heat reservoir, like the ocean. Okay, so the cycle exchanges heat with fewer than 2 heat reservoirs and produces work. The most important word in this entire statement, impossible. Okay, it's not possible. So what Carnot is doing here is he's saying that, and by the way, I'm getting goosebumps just talking about this. How often do you find the word impossible in a physical law? Like almost never, right? It's like saying never. This is a really powerful word. In other words, this will never happen. And as far as we can tell, it hasn't happened. All right, diagramming. All right, so let's draw a heat reservoir. I usually draw a heat reservoir as just a big bin here, and I say it's at some temperature. Okay, I'm going to mark it as a temperature. So this is my heat reservoir. Now, in this statement, note that he says fewer than 2. Okay, so in other words, 1 or none. Okay, so here's going to be my cyclic process. I'm just going to draw it as a circle, something that returns to its original state and repeats. Okay, so a cyclic process might be something like this. Right, this is the piston cylinder device. This is the thing that's undergoing the changes. Okay, you might think of it as the engine or the motor or right. It's a thing that's reciprocating. All right, so this is our work. This is the thing that's doing the work and undergoing the cyclic process. So, for example, you could think of it as an engine. Okay, so what Carnot says is a cyclic process whose only result is to exchange heat with fewer than 2, which I have here. For example, if I draw heat coming in from here to here, I'm going to do that. I'm going to call it Q. And then I'm going to say work comes out this way, W, like so. He says that's impossible. It's not possible. Note, it does seem to obey the law, the first law, right? In other words, if I think about my system, here, right? This is generally my system. It took in some heat, it gave out some work. Right? If these two were equal, it would be able to return to its original values. Right now, if these weren't equal, then I don't think this could really be a cycle, could it? Right? It would have taken in more heat and not produced as much work. That would have been weird. Now that means this thing's heated up. It's not going to stay at it. It's not going to be able to return to its original values. So if Q and W are the same, in principle, the first law says that Q equals W is totally fine. The first law says I can conserve energy by taking in heat and making it into work. But he says, no, you can't do that. It's not possible. Here's some other diagrammatic ways of thinking about this that are also likewise impossible. I'm going to get rid of this now and get rid of this. I did just erase my delta E equals Q plus W. And in the case of a cycle, delta E is 0, typically, right? It's returned to its original state. So through one cycle, there's no change in the internal energy. Maybe it changed a bunch during the cycle, but when it got back to its original values, there's no change. So if Q is equal to W, that totally satisfies the first law, but it doesn't satisfy the second law. At least the way Carnot wrote it. Here's another way of diagrammatically representing. Here's another situation here. Right? That would be a situation where there was exchanging heat with fewer than 2 heat reservoirs. I'm exchanging heat with none. There's no heat reservoir change exchanging here, right? This is just work coming out. This clearly violates the first law, right? That wouldn't happen by the first law. Another one, let's see, something like this, where I would do T and my reservoir like this. Okay, here's another situation. This also violates the first law. Okay, this also violates the first law. This thing cannot return to its original state if it has given up heat and done work. It's at a loss, right? It's at an energy loss. So it's not going to be able to return to its first state, its original state. So these two also violate the first law, but this one doesn't. This one violates the second law, but not the first law. So we have to say this is impossible via second law reasoning, and we'll get to why. Okay, so here's this. That's the Carnot statement. The Kelvin statement to the second law was that it is not possible to extract heat from a heat reservoir and produce work. I will write it for you here. So you can see it's a bit of a subset of the Carnot statement. Whoa, impossible. All right, so there it is again, that word impossible. Kelvin is making a little bit more of a bold strike, though it is a, like I said, subset of what Carnot said here. And you can see that what Kelvin is saying is same thing, cyclic process, whose only result now is to extract heat from a heat reservoir, which means, right, heat's coming out. It's not this one. This is adding heat to a reservoir. If you're extracting heat from a heat reservoir and producing work, no. In other words, it's a single heat reservoir. No, cannot do that. So Kelvin is being very specific to this situation right here. This one is what Kelvin is getting after, all right? Because he already knows that by the first law reasoning, which, by the way, Carnot didn't know the first law, right? But Kelvin does. Kelvin came along just after the first law. Well, actually, he helped make the first law, if you like. And he knows the first law is going to say no to these anyway. So he's not going to waste his time bothering with these things. They're already forbidden. He wants to specifically hit this thing, right? And that's the one that he wants to say, yeah, think about that. No, that's a no. All right? So Kelvin had the first law in mind when he wrote his. Carnot didn't. I've got one more to give you here, and it's the Clausius statement on the second law, which I think maybe I could fit in up in here. Likewise, came around just about also the same time as the first law, so this is a little bit post first law. Around 1850, not 1950. That would have been too much. Clausius. So Clausius's statement is interesting. It's one that we haven't hit so far, which is why it's a fun thing to do. Okay, so here it is. So you can see they all have kind of the same wording. So but that's very specific, right? A cyclic process whose the only result is to extract heat from a heat reservoir and then reject it to a hotter heat reservoir. Reservoir is impossible. All right, let's see. How did I do here? Reject heat to a hotter heat. Yep. So Clausius is saying a cyclic process whose only result is to extract heat from a single heat reservoir, but then reject it to something that's hotter is impossible. This is a really fun statement because I'll diagram this out for you here. Let's do it this way. Okay, so here is a heat reservoir at some temperature. Here's a heat reservoir. I'll do it down here. Here's a heat reservoir. Let's say this top one is the hotter one. I'm going to call this H. This is the hot. This is the warmer one, hotter one up here. This is the cooler one down here. I'll call this TC for T cold. And then here's my cyclic process in the middle. Now, what does it say? A cyclic process whose only result is to extract heat from a heat reservoir and then reject it to the hotter heat reservoir. In other words, extract heat from here. I'm going to call that QC from the cold temperature reservoir. It's now going to reject that heat into the hot reservoir, thus making the cold thing colder and the hot thing hotter. Now, that is not allowed. In other words, this is the wrong way for heat to flow spontaneously, right? This is not the way it goes. Heat should be going this way, not this way. Now remember, it says its only result is to do this. That means that we have not supplied any work to this, right? It doesn't say anything about taking in work. It says its only result is to do that and then that. So that's a no. Now, however, if we put work into the cyclic process, now we have a refrigerator, okay? So with the work input, this is totally allowed, but that's not what Clausius is saying. Clausius is saying the only result is that, and that's not going to happen. And so far, we don't seem to observe heat going the wrong way. So cold to hot, no. All right. All righty. So we have these three statements of the second law. Okay. Now, notice, I don't know if any of you are familiar with thermodynamics as it is kind of presented in the modern way. that the second law usually talks about it's known as the increase in entropy law. Nowhere have I talked about entropy. Okay, so entropy is really a sidebar to all of this stuff. The second law's main focus, when it was first established, to get right down to what is the second law's job, it's to put limits on how energy can flow. The first law's job is to tell us that energy can flow from one thing to another and say, hey, this is going to drop in energy if energy comes out, right? In other words, if I run a marathon, I better eat something. I need to put energy in order to run, because that's my internal energy is dropping as I'm using it to power my muscles, okay? So the first law tells us that energy can drop and increase and get transferred, and it all adds up perfectly. But the second law's job is to tell us what is not allowed. Now, this seems like it should be allowed just fine from a first law perspective, right? There's a heat transfer, there's a heat transfer, right? They're the same size. This one drops in temperature, this one rises in temperature. Nothing wrong with this according to the first law, okay? So the second law's job is to say, no, that's not an allowed energy flow, okay? Now, you might ask, well, why is it not? Because it isn't. We never observe it. That's why it's not allowed, because we've never seen it. And not that we're the be-all, end-all of things, but apparently it seems to work okay. We haven't seen it. All right, so this second law gives us the ability now to define things like the entropy, the efficiency of a cycle, right? It also gives us the ability to define temperature in a more rigorous way than the zeroth law did, okay? So we have the ability to define a thermodynamic temperature based on the operations of a heat engine between two heat reservoirs. Okay. Okay, so we're here, and now what I want to do is, I guess let's hit the third law real quick, because we've spent a little bit of time on the second law, and then we'll get into doing some consequences. All right, so let's do this. The third law is one of those that's kind of like the zeroth. I said before that most of our calculating and thinking is going to be spent on laws 1 and 2. All right, so law 0 was there just to establish there's something called thermal equilibrium. Okay, fine, we know that. And there's something called temperature. Great, we know that. Law 3 is here to tell us something about what happens when things get kind of cold, and it's just there to make sure that we're operating within what apparently seems to be the bounds of our observations of nature. So this comes about from a couple of different people. Walter Nernst is one of the first originators of this. So it's known as the Nernst postulate. It did get elevated to a law, and I'm not entirely sure how, but that is a very interesting story in and of itself. Max Planck, who we will refer to when we get to the modern physics stage, is also known as the Planck hypothesis. So like I said, these two folks were just kind of trying to throw some stuff out there. All of a sudden, this got made into a law, and hey, happy days. All right, so no problems. Let me give you the quick and dirty Cliff version of this, because it's a little bit out there. Essentially, it's telling us, this is known as the law of unattainability. All right, so no reversible process. And I should define reversible for you, and I will in a little while after I'm done writing all of this stuff. No reversible process that is adiabatic. Can take a system of non-zero temperature. So I'm paraphrasing a bit here, but essentially that's going to do it. All right, so this is known as the unattainability law. No reversible process, or say no adiabatic reversible process, can take a system of non-zero temperature and take it all the way to zero temperature. Let's first understand that we are talking about the absolute temperature scale here, okay? So when we talk about temperature, just real quick, in case you are not familiar with this, which you may or may not be, we have a couple of different ways of measuring temperature. Here in the United States, we typically use the Fahrenheit scale, which is a degree scale. And I don't really know what a degree means, where some people make a big deal out of there being degrees of this and there are no degrees of that. I don't understand. It seems, and I think it's probably just pedantic, but that's okay. We measure temperature in the degrees Fahrenheit scale. I'll make that a little larger so you can see. Degrees Fahrenheit, in which we have water freezing at 32 Fahrenheit. We have water boiling at 212 Fahrenheit. A hot day is typically in the 90s, possibly hundreds, depending on where you live. Although around here, it's also hot in the 80s. And apparently, according to my daughter, it's freezing when it hits 50. So depends where your mind is, I guess. But nonetheless, so we have that. We also have the centigrade temperature scale. The centigrade is the metric equivalent, and it will freeze water at 0 centigrade and boil water at 100 centigrade. And that's great. A hot day would be probably in the upper 30s to low 40s. That would be a sizzler. Typical room temperature you're going to look at, if you think of like 70 degrees Fahrenheit as being a kind of like that's about 68, 70 degrees. That's like a nice room temperature, maybe 72. If you're from LA, it's sunny and 72. That's going to run around 20, maybe centigrades, about 20 centigrade, maybe a little bit more, 25, say, right in there. It's going to be kind of like good range for room temperature. We also have what is known as the Kelvin scale, okay? Now, this is one you may not have heard of, but is also known as the absolute temperature scale. Okay? Now, it gets down to a bit of thinking about what's going on when we say temperature. So, to skip ahead a little bit, actually to take a quick deviation away completely, what we find is that temperature, and by the way, this right here is a synopsis of probably thousands of years worth of trying to figure out what temperature means. What does hot and cold actually mean? This is a horrendously difficult question if you have nothing to go by. So people have been struggling with this for a long time, okay? And it wasn't until Fahrenheit came along. That's why we have the Fahrenheit scale. And tried to deduce something about, okay, what does this mean? What does this mean? And how does this work? And he was actually a pioneer in some refrigeration techniques as well. Here, the Kelvin scale is a recognition that if I take take an ideal gas, that's the easiest thing to think about. An ideal gas, it's a gas in which there are no molecular or atomic, whatever the constituents of the gas are. There are no interactions at all until something physically hits something else. Okay, so in other words, there's no bonding. Okay, there are no bonds between the gas molecules. So they are not interacting until they whack into each other. Okay, when that happens, when we think about the energies of those things, we're going to think about kinetic only, because there's no bonding, there's no potential energy between the atoms or between the molecules to cause them to bond together. There's zero potential energy. There is, however, when you heat something up, a lot of this random motion, okay, discovered by a fellow by the name of Robert Brown, and is known as the Brownian motion. There is a lot of random molecular motion when something is hot. So the Kelvin scale says, what's happening when we take all that motion away? If something is at zero kinetic energy, then that's the lowest possible temperature that you could reach. That's why it's called the absolute scale. There's a floor to how cold things can get. And that is when the constituents, atoms, molecules, whatever it is, stop moving, right? You can't have anything less than not moving. You can't have a negative temperature. So if you just say that's zero, you can't do any worse than that. Okay, so that's what this is referring to. You cannot take a system to zero temperature. In other words, that idea of zero kinetic energy in the molecules is not attainable. It would not, you wouldn't be able to get there. Now, we have gotten close, but to reach absolute zero, no, we haven't, and I don't think we ever will. I think it's like I said, it's not attainable. Okay, so we've got those going, and that zero temperature and non-zero temperature refer to the temperature scale in the Kelvin degrees. Okay. All right, so those are the laws. 0, 1, 2, and 3. Those are the laws of thermodynamics, and our goal in the next few weeks is to obey them, because that's what we have to do, apparently. All right, so let's start talking a little bit about, let's start dissecting the first law. But oh, you know what? Before we do that, I want to do this. I don't know. Because it's such, so I'll give you a little bit of background here. This is a fun class for me to teach. This is the unit that I've been looking forward to the most. I always do, because this was basically what I did my PhD in. Okay, was thermal physics, okay, like this. And I happen to think that there's no better subject. So I have a couple of, I compiled a couple of quotes here from some of the physicists who perhaps you've heard of through time, or perhaps not. But I thought I'd read them to you because it helps to express a little bit of why we think this is a fantastic subject. So we'll start with Einstein. Right? We'll start with Einstein, as you have to. Einstein says, thermodynamics alone amongst physical theories will never be overthrown. Now, this is from a person who basically told us that Newtonian mechanics was not quite right. So that's kind of a big deal. He's taking the ideas that we have of motion and saying, no, it's actually this way. He's saying, this subject is never going to happen. That's a big statement from a guy who kind of made a specialty in overthrowing stuff. Here is a quote from Sommerfeld. This is Arnold Sommerfeld. You may not have heard of him. This can be, take it or leave it. I thought it was funny. He says, the first time you go through thermodynamics, you don't understand it. The second time you go through thermodynamics, you think you understand most of it. Then the third time you go through thermodynamics, you know you understand none of it. But it doesn't bother you because you're used to it by now. So there's that. Eddington, Sir Arthur Eddington, one of the pioneers of experimental tests in general relativity in the late 1915, 16, 17s, right around there. And a famous astronomer and physicist in his own right, says entropy increase holds supreme position amongst the laws of nature. In other words, what he's saying is there's nothing better than law 2. And you know what? I agree with him. I also wrote something down of my own, which is that thermodynamics is a deeply beautiful and subtle science whose true depth of both consequence and character cannot possibly be revealed in 5 weeks, which is the time we have to do this. So that is one reason why I both enjoy doing this and do not enjoy doing this. We've only got a certain amount of time. And so I can't really show you how great this is, at least from my perspective. Anyways, with all that whining out of the way, let's get on to dissecting the first law a little bit and look at what we have in terms of the 3 quantities that the first law addresses. Okay, so our first law in mathematical form relates the internal energy of a system, right? This is why the system is so important to have in mind, right? The internal energy of my system is going to be changed by heat and or work. Okay, so that's heat, that's work, and this is the change in the internal energy. This is predicated on the idea that you have selected a system, because outside that system is where the heat and work are coming from, right? It's not coming from inside the system, it's coming from outside, it's going across the boundaries that you have decided upon. Okay, so if you have thought about your boundaries, and who doesn't, you might make them adiabatic, in which case there will be no heat coming into your system. You have prevented that. There may be rigid boundaries, in which case there will be no work coming into your system, right? So you can isolate your system through appropriate choice of boundaries. Nonetheless, if you don't, and one of these or both creep in, you will change the internal energy of your system. So let's dissect these things a little bit and figure out what we can about what's going on. I think before I get anywhere further, I'm going to talk about what system typically we do want to talk about, all right? And in this class, we have one that is going to stand more head and shoulders above others. I don't want to say it's more supreme, but this is the one that we're going to spend a lot of time on because of its simplicity, okay? And the system is going to be the ideal gas. Okay, what is an ideal gas? I kind of just described it for you. Okay, it's a gas in which there's no potential energy between the things, the particles that make it up. And I even don't want to say particles because you think that means they're kind of like dust. It's not. I mean the atoms or molecules that make up the ideal gas. And the reason for that is because its equation of state and its state variables hopefully are relatively intuitive to us, okay? And they're relatively simplistic. Every other system is harder than this one, so that's why we're choosing this one. The ideal gas, it's a collection of one or more, I guess, could be multiple chemical species. Man, this pen is having a lot of trouble spelling today. Species. It's a collection of one or more chemical species that have no interaction unless they are physically touching, right? In other words, there's no potential energy between them. Or more, more chemical species with no potential energy between them. Okay, so I consider this, there are several phrases to describe this. I consider this the exact situation of the billiard ball table, right? You go play pool, the billiard balls, they don't know anything about any other one until they hit, right? Or they hit the walls of the container, right? They hit the boundaries, the bumpers. So this is what I mean by ideal gas, is the pool table, okay? We're going to focus on that as a system or as a yeah, I guess as a system because of its simplicity. Let's go here and do this. Let's get rid of this and that. Okay. All right, so that's why when I was talking about the absolute temperature, you think about the internal energy of one of these things. What kind of energy is it? It's got to be kinetic. There's no potential, right? Well, how many kinds of energies are there really? Well, there's stuff moving around, kinetic. There's stuff interacting, like gravitational potential, electrical potential, if you like, magnetic potential, nuclear potential. Uh, they're all potential energies, spring potential energy, elastic potential energy. These are all potential energies. Okay? If we eliminate those as an entire, right? If there's no potential energy between these, well, we've eliminated everything but kinetic. So that's it. If I put heat into this thing, they speed up. The little thingies, speed up. And I will say this also as a mentality. Our subject, as of right now, classical thermodynamics is what this is called, makes no reference to what these things are. Atoms, molecules, no. True basis for understanding of atoms and molecules did not arrive until the late 1905s, after 1900, right? We're talking about happening in the 1800s. This is classical. Starting around 1905, that's when the modern era started. We're before that. So these atom things are very strange to us. We do not know what they are. Okay, now that's if you're going to go by the book, that's what classical means, classical thermodynamics. Now we obviously know better than that, so we are going to talk about them, but I just want to let you know that sometimes you get into this mindset like, wait, we don't know what these are classically. Okay, all right, fine. Internal energy of an ideal gas is therefore all kinetic. But is all kinetic energy, right? It's the movement. Kinetic energy. It's the movement of these things, right? They're buzzing around, bapping into things. So that when we think about an internal energy of a gas, then when we heat it or do work on it, its temperature goes up because there's no other place for the energy to go. It's going to have to go into the kinetic energy. Okay, so any change in internal energy results in a change in the temperature of the gas. Now, I do want to make it clear of the ideal gas. I do want to make it clear that we are only talking about ideal gases here. Okay. In this case, when I talk about other situations, there could be other systems. We will talk about water. We will do things, but our calculations are mostly going to be centered around the ideal gas. And therefore, our thinking is going to be centered around ideal gas. But I do also want to introduce other substances so that there is the possibility of, well, wait a minute, if we put energy into this and it doesn't heat up, what does that mean? Okay, so I do want to explore other possibilities. I just want to be real clear. This is only for ideal gas. Okay, these two things right here are only for ideal gases. So make sure that you have these underlined in those because they are not true in general. Okay. All right, so let's start with work. Let's see, how much time do I have left here? Actually, probably not a whole lot. Well, this is what happens when you get to something that the instructor really likes. He goes talking about it for so long. Let's talk about work, and then we'll spend a few minutes on this. I guess we'll be done for today. Let's talk about work. Let's talk about work as you probably know, right? When I have work done on something, there's a force. If I just draw this box right here, right? And the box displaces. I'm going to run out of space here, so this is a stupid place to draw this. Right? If I have a force right? Here's a box. I'm pushing the box, and the box goes from here to here, right? And I push the box with the force, then the work done in this case, you'd be able to decipher as being force times D, right? And if you had 4A and you explored other forces which could be changing, or maybe the distance isn't quite always in the same direction, then you came across this idea that the work is really an integral of F dot dr, or ds if you prefer, whatever you like. But we've chunked up, right, this distance into small little drs, like that. And we are doing a dot product between the force involved and the differentially small displacement of the box, okay? So when we add up all those little differential chunks, then we get the total work done, all right? Now, in the case of a gas, it's going to be very useful to deal with state variables that are more directed towards what a gas does, or in general, a fluid, right? We can talk about forces and displacements, but it's way easier if we're going to talk about pressures involved and volumes instead of forces and displacements, okay? So we can actually modify this a little bit in order to take into account the idea that we are talking about a fluid, okay? So into this, we are going to put the idea that the force is really the same thing as a pressure multiplied by an area. Okay, and so I want to talk about the force involved as being a pressure, as being due to a pressure, or perhaps a pressure difference would be a better way to think about it, a pressure difference. And therefore, I want to think about, instead of not just the displacement, I can think about the displacement, but now I'm going to take this area and I'm going to absorb it into this displacement so that I have an area that's displacing a little bit, right? Like I take this big rubber sheet of something that's separating that from this, and I move the whole thing a little bit, right? That's a big area that's displaced slightly. I've just created a volume displacement here, yeah? I've just increased the volume of one side and decreased it of the other side, right? So if I do this, then what we can do is we can morph this F dot dr, which is not useful in a fluid sense, into a P for pressure, right? P for pressure dV. And I'm going to use bars here to denote P for pressure instead of momentum, and V for volume instead of velocity, all right? This is, in other words, pressure like this, D volume. Pressure D volume. I don't know, D volume. I don't know if you can really write that. Oh well, we just did. Cool. All right. Because of the state variables of the ideal gas, pressure being one of them and volume being another one, this is going to really help us out in the way we think about work being done on an ideal gas. All right. Now, again, I want to encourage thinking about ideal gases, but I also want to not restrict us only to ideal gases, okay? So I want to think about bigger things, not just ideal gases. But the good news is this is a general situation. I haven't said that has to be true only for an ideal gas. This is true in general for anything which we can represent with a pressure and a volume, and that also includes liquids, okay? But anyways, or even gases in which there is some potential energy between them. Nonetheless, I think that's probably about it for today. And we'll get into a little bit more of the nuts and bolts of the first law starting tomorrow. We'll get a couple of examples and start looking at the drawings that we are going to be doing, okay? So the drawings, like including the heats and the cycle processes, the heat reservoirs, we're going to start including energy bar charts, and we're going to also go to PV diagrams, which will be very useful. But until then, we will call it good for today. So go enjoy a thermodynamic day and study up, and I will talk to you next time. All righty, see you folks.